complexity generators.
Yes, thank you for the introduction.
This opportunity and to say hello to other participants who I didn't have a chance to meet since my arrival yesterday. So proof complexity generators is a valid title because I'll eventually mention one, but it's not really that descriptive because I want rather than about some technical point to speak about sort of big picture where this falls in. So the problem I'm very much interested in with other people, I suppose, is whether NP is or is not equal to its to co-NP, and to motivate or to explain what type of results I would like to get about this result, let me look at several other central problems in complexity theory. So of course, first of all, whether P equals NP, and then we may ask about the power of randomized computations, and that would be the question whether P equals BPP. And then another type of applications or important assumption in complexity theory have to do with cryptography. So for example, the question whether there exists one-way function, or even better, one-way permutation, or whether there exists pseudo-random number generator, and maybe even strong whether, say, public key cryptography is possible. So all sorts of questions one remain open. Now, the difference between this question and these others I listed here is that we know answer to these if we assume some hardness hypothesis about sizes of circuits. So for example, of course, the MP completeness will tell us that P is different from NP, assuming that every circuit computing specific function sat on inputs of length n has to be large. Now, for the other problems I wrote here, the similar results are known. So for example, it's known that the randomized computations, at least in the formalization of BPP and polynomial time, are not stronger than the deterministic one if every circuit computing, I mean, you probably cannot read this, but it will repeat several times, so you will remember it. So every circuit computing, say, the complete or a complete language for the exponential time e needs circuits of size which are also exponential in this particular form 2 to the some delta times n. So this was proved by Impagliazzo and Wittgerson. Using earlier work of Nissan and Wittgerson on the famous generators about. Okay. Now the existence of pseudorandom generators and more generally about the existence of various constructions which are of secure cryptographic protocols. So let me just write this. There exists pseudorandom generator, public key possible. So that follows if again every circuit computing factoring has to be large, and now large means exponential in this form, and computing means not just computing exactly, but you have as in cryptography, that every circuit which would compute it with a non-negligible advantage should be large. Okay, so these are diverse problems having to do with the power of deterministic, probabilistic computations and cryptographic assumptions, and they all follow from the same type of assumption. So the assumption has the following form. So say general form. Every circuit computing, say, task T has to be large. Now what changes is what is the task, whether you should compute exactly SAT or even with high probability factor, and what does it mean large? Sometimes it means just super polynomial, and sometimes it means exponential with different interpretation what exponential means. But what is important is that the computational model here, the computational hardness assumption, talks about the same model all the time, ordinary deterministic Boolean circuit. Okay, and so the question I'm interested in, if one can resolve the NP-co-NP question assuming something similar. So is there something of the same form which would imply that NP is different from co-NP? So that's the problem I'm interested in some kind of general terms. Now the approach to this is via proof complexity, and that will just use a simple characterization due to Cook and Rekov, which is perhaps known to most of you, that the question whether NP is equal to co-NP is simply a question whether there is a propositional proof system which is polynomially bounded, where all tautologies have proofs bounded by a polynomial in its size. So just a brief definition, say a binary relation, a p time, is propositional proof system if you have the property that, say, X is a tautology in some natural encoding if and only if there exists Y which witnesses it, and it is R is P bounded if you can plug here some a priori bound in terms of X, a priori polynomial bound. So in this very general definition, it's obvious that tautologies are in NP if and only if such an object exists. So this might look, unpleasantly general, but in fact, if one considers propositional proof system in this very general sense, one can show that in certain, well-defined sense, they are equivalent. Any such system is equivalent to taking the usual textbook propositional calculus, modus ponens, finite number of axioms, and perhaps adding to it a sparse set of extra tautologies as axioms, and this system will then what is called simulate any other given system. So in fact, it's enough to think in this context about the propositional calculi as we are used to. Okay? So if you look at it in this way, then the task I am interested in means that you want to use some hardness assumption of the form as in the box and show that no proof system is polynomially bounded. And so in particular, it could happen that you may construct a sequence of hard tautologies say tau n in x1 up to xn, such that for any propositional proof system R, the box assumption would imply that R proofs, that mean the witness is Y from the blackboard above, of tau n's cannot be polynomially bounded. So one has to do two things. First thing is to produce actually sensible candidate formulas, and that's what I'll mention about a little bit later. And the second thing is actually to make this implication work from some assumption. Okay, so if you look at this implication contrapositively, what you want is that having short proofs of some tautologies, from that you should be extract some computational process, some computational information which should contradict some hypothesis about hardness of certain task. Okay. Now, so before I'll explain for what type of formulas one looks here, let me give an example where this second idea, extracting computational information from short proofs, actually works. And that's the example of the so-called feasible interpolation. So, feasible interpolation is the following idea. So, assume you have, say, pi, an R proof in some proof system of, say, formulas, say, alpha xy or beta xz with the usual disjointness. Y's don't appear in beta and z's don't appear in x. And what you want is that there is an algorithm which takes pi as advice and on input x produces a proof of either alpha or beta. So on input a triple A is substituted for x, output is an R proof of either this or this. Okay. And so this allows to, that's like in Craig interpolation, except the additional information is that the proof system has such a form that if you have a proof, you can from the proof extract an algorithm, and the algorithm will be feasible. So that means if this has some size s, the algorithm will run in, say, time polynomial in s. So feasible, whatever that means. Okay.
So feasible means what's polynomial in this?
Well, so feasible in this context, feasible means polynomial in the size of the proof. Okay. Now, so if you look at it in this way, then it's easy to see what kind of formulas will become hard if you have this property, and how you extract, and what is the computational hypothesis extracted from such proofs. Namely, let's take two disjoint NP sets, U and V, disjoint, and assume that this is defined by property there exists y alpha xy. I'm skipping out the bounds, and there exists z beta xz. So the disjoint, well, okay, negation of that. So the disjointness of U and V is exactly the property that disjunction is tautology. And so if I'll prove the disjointness of such two sets, then I have an algorithm which takes little time, takes the proof as an advice, so it will be a non-uniform algorithm, but on an input it's able to separate the two sets from each other. So if you use some assumption, and here comes, for example, the existence of one-way permutation, or the hardness of some encryption scheme where the two sets would be whether you are encrypting zeros or ones and similar, then if you simply, the assumption is that there will be two disjoint NP sets which cannot be separated by small circuits, then from that you derive that the statement the disjunction has to have a long proof in any proof system which has feasible interpolation. Okay. Now, so this is an idea which works in surprisingly many different situations, starting from resolution, cutting planes, Lovász-Schreiber relaxation, some algebraic proof system working with OBDDs and so on. But it probably does not work for a too strong proof system like is, for example, the Hilbert style textbook calculus. So one wants simply different situation, but somehow this is an illustration that the general idea is, maybe possible. So let me now explain what are the formulas which we consider in this respect for the general proof system. So I said before, what we need are formulas, and we need some reduction or method for establishing this implication. And so I will now talk about the formulas. The method for that is using links of propositional proof system with bounded arithmetic and some model theory, at least the proposed method, and I will allude to it or talk about it a little bit on Monday in the workshop, so I will skip that today. So let me now consider the formulas. So the formulas will be as follows. So assume you have a map which is computed, say, from n bits to n plus 1 bits. And this map is in NP intersect co-NP. So what I mean by this, let me just write it explicitly down. What I mean by that is that for all I can say that the ith bit of output is 1 in an NP way. So this will be if and only if, say, how should I call it, AI x yi is satisfiable, and that it is 0, I will say in a similar form, but just the index will change to 0. And these formulas have size, which is polynomial in the length of input, which is n. Okay. So you have this setup, and now take any string b of length n plus 1, which is not in the range of this function. So at least half of them are outside of range. And then write this property that it is outside of a range as a tautology. And so the tautology, which is often denoted like this, is simply the following disjunction. Disjunction over all possible input bits, and the disjunction says that at least on input x, at least one of the output bit has to be incorrect. It doesn't give b. So it says the following. Okay. So it says whatever for every x and any possible witnesses, there will be one I such that no yi can witness that the output is what it is in B. There will be at least one output string, output bit of the function value on x, which differs from the corresponding bit in B. Okay, and because bi can be either 0 or 1, but we have an NP way of defining both bits, so this is really just a propositional formula, and the property that it is outside of the range is equivalent to the fact that this formula is a tautology. Okay. So this is a type of formulas which one considers. Now, of course, the devil is in choosing the right function f, and the right function f seems to be the one suggested in a little bit different context by Rasborov, namely the ordinary Nissan-Wittgerson generator, but based on a NP-CoNP function, and in fact one needs a little bit more. It's based on the hard bit of one-way permutation for some results. Now let me mention just type of this box, the hardness assumption one gets to. So let me first write what is this. So f of x is the Nissan-Wittgerson generator based on a hard bit of a one-way permutation. Okay. Now let me allude to the problem whose hardness is needed in the corresponding situation here, and which allows to make, excuse me?
We don't know that there exists
we don't know whether there exists a one-way permutation, right? So this will sit in this box of the hardness assumptions, okay? So we don't know, well, whether these formulas are, we cannot prove that these formulas are indeed hard for all proof systems, but in this method about which I'm saying nothing, in certain model theoretic constructions, there are two conjectured steps what could be done, and the first one can be done under certain box assumption. And so what I now want to explain is not the link to bounded arithmetic and to model theory, because there is no time for it, but what does this assumption says? Okay, and this assumption says that in a certain two-player game, the strategy of one player, if he should win, has to be computed by a very large circuit. And this assumption itself follows, in fact, from the existence of one-way permutation alone, but it has to be one-way permutation in the cryptographic sense, namely that every circuit which computes it with a negligible non-negligible advantage over 1/2 has to be large. In the feasible interpolation, we just needed that every circuit which inverts, say, one-way permutation everywhere would have to be hard. In these things, you need more, you need the cryptographic properties. Okay, and so what is the game? The game is actually very easy. So you imagine that you have this, possible x of length n, and here are the bits b1, b2 of some string which is outside of the range, and now the players will get some assignment a for x's, and the first player, the student, is supposed to find a bit of the output which is incorrectly computed. It doesn't equal to corresponding bit bi in string b. Now, because he is just a circuit, he cannot compute this NP-CoNP function. So he computes some candidate value I1, and then he will ask the second player, called the teacher, who will give him a witness for the value. So the teacher will provide some y, which witnesses in the sense that the formula is satisfiable, and that means that the value is 0 or 1. So if the student actually manages to find an incorrect bit, the teacher says so, and the game finishes and the student won. If not, he will get a witness while his answer is incorrect, and then he will compute another value where he can use not only the x, the input, but also the witness he got in the first round from the teacher. Okay, and the hardness assumption you need for the construction in model theory, about which I'm saying nothing, is that every student who manages to win this game on every input in a fixed constant number of steps has to be exponentially large circuit. And so that's the assumption. So this, what I just said, is actually what I would consider a valid assumption, assuming that you sort of convince yourself that it's plausible, because it is of the form of this general box. Every circuit doing something specific has to be large. But in fact, in this in this case, one can use some reduction to the ordinary cryptographic assumptions that one-way permutation exists using the properties of the Nissan-Wittgerson generators and so on. So this is the type of things I'm interested in, and I understand that's the point of this seminar, talking about that rather than some incremental technical progress. I would simply be interested in reducing this fundamental problem to some hardness assumption like this. So thanks very much.
Are there any questions? Yes.
Would it help you to get advice bits?
Well, they come they come in proof here, because in the reduction of this box to this, you fit.
If instead of just proving hardness relative to circuits, you get a stronger assumption, which is you use hardness with advice bits.
Well, the circuit is the advice bit. The circuits are non-uniform in this setting. So
They're non-uniform.
yeah,
Right.
so sorry, they are non-uniform. Yeah. So when I speak about circuits, I mean non-uniform.
No, then
type.
advice bits don't matter. Absolutely.
Yeah.
More questions? Or? So maybe you can elaborate a bit. There was one point you mentioned when you discussed this result by Cook and Rekov. You said that if there is an efficient proof system in general, then you can actually choose it to be like a Frege system with some sparse set of actions.
Okay.
Would that would not apply to bounded depth Frege? Is it correct? That kind of statement.
No, I think it would actually apply to anything little over resolution.
Okay.
But maybe let me just explain analogy which is clear to everybody. So if you have some theory in, say, language of arithmetic, and you are just interested in proofs of its pi 0 1 consequences, then it's enough to take some basic theory and add consistency of t, and it will also prove pi, right? All pi 1 consequences are provable from consistency of t. That's sort of easy exercise over some fixed theory, I don't know, bounded arithmetic or I sigma 1. The point here is the provable sigma 1 completeness. Okay. Now, so in the propositional case, something similar happens exactly. You take arbitrary proof systems and you look at proofs of tau, and instead of it you take some basic system, and I think it can be a little bit over resolution, and you add formulas which say that R is sound proof system, that whatever it proves is a tautology. And then proving a tautology simply means taking the proof here, plugging it into corresponding soundness statement, and then just use something like Tarski's true definition like here. So it is it's not informative in the sense that the extra set of formulas would have some combinatorial meaning. I mean, it often does for a lot of proof systems, but for a general algorithm we don't know. But it is at least, you know, at least we can concentrate just on proving Clover bounds, say for the Hilbert-Stahl textbook calculus, and we don't know that either. For the propositional logic based on say finite number of axiom schemes and modus ponens and so on, we only know quadratic Clover bound, and that holds for trivial reasons, so I will not even explain it. I hope it's not somebody's theorem.
Okay. Thank you very much for.
Thank you.